Algebra 1, Polynomials, KCS at Home, Summer Edition, Part 3. Didn't quite finish Polynomials in Part 2, so I thought we would pick up right where we left off, except I thought maybe we would do a quick review. So one thing about factoring is you really have to understand like which world you're in. When you look at a problem, you got to think, am I doing a greatest common factor? It's the first thing you should always check. Am I thinking about this more of like a quadratic coefficient of 1 or more of like the AC method that requires group factoring? Or is this more using difference in perfect squares? And so let's walk through 4 of those examples just to kind of see what I'm talking about. So the first one, I see 24x to the 4th minus 27x. First of all, power of 4 a little high for beginning a quadratic, so the first thing I look for is GCF in that, especially since 24 and 27 both are multiples of 3, and they both have variables. They both have x in them, x to the 4th and just an x. So I think for my GCF choice here, I want to say, well, they both have 3x as a common factor, and it's the greatest common factor that they have. And then I want to start dividing. 24 divided by 3 is 8. Subtract 4 and 1 for x to the 3rd. And so again, if you multiply 3x times 8x to the 3rd, that's going to give you 24x to the 4th. And then using that 3x again with division with this negative 27. Negative 27 divided 3 is negative 9. And then those x's kind of cancel out there when you divide. And so checking with distribution, this will factor perfectly. Now this is more of a coefficient of 1. They do not have any greatest common factor, so they all do not contain x. 2 of them do, but that last one doesn't. 1, 7, and 12, they do not have any common factors involved, so this is more of that coefficient of 1. What's going to multiply to be 12 while adding to be 7? So we kind of talked about that box method. But eventually you just want to be able to say, well, that would be 3 plus 4 is 7, or 3 times 4 is 12, and being able to build your factors as x plus 3 and x plus 4. Multiply them together to check it if you'd like. And so a similar problem on the left is they do not have a greatest common factor. They don't all have x or anything like that. This is where you would have to go through a similar process, but you would need to start by multiplying your a and your c term together. 2 and negative 3 multiply to be negative 6. And now I'm trying to look in that middle value. Looks like there's a negative 1 for b that I'm trying to add to b. And so let's think about, well, what would multiply to be negative 6 while adding to be negative 1? And as I think about that, I'm thinking about 3 and 2, but really negative 3 and positive 2. Those values really accomplish both goals of multiplying to be negative 6 and adding to be negative 1. So now I really want to use those terms to replace the middle. So negative 3x plus 2x. And then you're in terms of 2x squared and negative 3. Those don't have to change. Well, let's go for some greatest common factor here, kind of looking in groups. These first two have x in common. If you divide each of these by x, you get 2x minus 3. And if I look at this second grouping, they really only have a 1 in common for a factor. So now I notice that 2x minus 3 repeated itself. And then the x plus 1 that I took out, that can be my other binomial. And this creates my factored pairs. And where we left off in the last video kind of prompted me to do a quick review here is a difference in perfect squares. And you may say, well, Mr. Turner, 2 and 32 aren't perfect squares. I'd say you're correct. But we want to always look for a greatest common factor first. For example, if you were to divide everything by 2 here, that would leave x squared minus 16 into parentheses. And then if I start thinking kind of like the coefficient of 1, what would multiply to be negative 16, but my b value, that term that just has the x on it, is kind of missing here, meaning that my b value is 0. So what would multiply to be negative 16 but add to be 0? 4 and negative 4. So with these, it's all about that, perfect squares. The square root of 16 is 4, or the square root of 25 is 5. I wrote that just thinking about it. But really knowing those perfect squares will really help you factor those really well. So that's kind of what I did on part C here, taking out the 3 and then multiplying to be negative 100, you need positive 10 and negative 10. Now, I didn't do B. I kind of skipped over it because this one is actually not factorable. There's no way to rewrite this, and a lot of it stems because it's a plus in the middle. You may have thought when I said difference in perfect squares, difference is a minus sign or subtraction. So really, when you're looking for those perfect squares, you really do not want to see a plus between them. You're looking for that minus there. So let's do one more to kind of tie quadratics all together, especially when it comes to factoring. So it says, factoring a quadratic will reveal the roots or the zeros. So in our very first video, we talked about these terms, these vocabulary terms, are basically points that hit the x-axis, x-intercepts, if you will. And so factoring really helps reveal those values to us. And so we're going to factor the quadratic, and looking at this, it looks like there's no GCF in common. 6, 17, and 12 do not have any common factors. They also do not all have x in common. So I think I'm going to start by doing the AC method. 6 times 12 is 72. So what multiplies to be 72 while adding to be 17? So these may take you a moment, but you can start thinking, well, 1 times 72, that wouldn't add to be 17. Or, half of 72 is 36, 2 times 36. But that wouldn't work to be 17. Or you may just think about the multiplication table, like 9 times 8 is 72, and 9 plus 8 is also 17. So those are the numbers that I want to consider breaking up that middle term. I think we used to call it bust the B. So we're going to bust up that 17x and make it 9x and 8x, like two separate numbers that if they went together, they would be 17x, but we don't necessarily want to put them together. We separated them on purpose. So now I look at my groups, 6x squared and 9x. Those both have 3 in common, and they also have x. One has 2, the other one has 1. So basically I can divide an x off of each of these, and I'll be left with 2x plus 3. Now, if you're familiar with this process, I'm really expecting to get that 2x plus 3 again when it repeats. And so when I'm looking at 8x and 12 and thinking, well, those are both divisible by 4, well, 8 divides by 4, got the 2 with the x as well, and 12 divided by 4 is 3. So now we have our factor pairs. We have 2x plus 3, and we also have 3x plus 4. So now we can kind of start talking about, well, what's going to make these 0? And this takes some time to establish. But if you notice, these two parentheses are multiplying against each other. They're written against each other with no space in the middle, meaning these ideas are multiplying. And if you think, well, how do two things multiply to be 0? One of those numbers would have to actually be 0. So I'm going to set each of these equal to 0. 3x plus 4 equals 0. 2x plus 3 equals 0. And if I find out what makes the expression 0, then I have found one of those roots. So I want to subtract 4 to the other side. Let's divide by 3. And so negative 4/3, I mean, that's somewhere around here. That would be one of my zeros or my roots for my quadratic. Similarly, let's solve for x in the second one by subtracting 3 to the other side and divide by 2. And it looks like my other one is negative 3.5. So these are actually very close to each other. They are like almost hard to show you on this graph, but they basically both fall between negative 1 and negative 2. So I'm going to use the axis symmetry formula from that first video. If you remember that is negative b over 2a, you've got a really good memory. So a, b, and c here. B would be negative 17. And we're doing 2 times a, or 2 times 6. So that's negative 17 over 12. So this is definitely a tougher axis of symmetry problem, because negative 17 over 12, that's going to fall between these 2 points somewhere, and it's going to cut that quadratic in half. And so want to maybe use the graphing calculator a little bit, because these points are so close to each other, to really get an idea of what we're looking at. Let's go to our graphing calculator, And let's do 6x squared plus 17x plus 12, and let's look at a graph for that. So just like I was saying, those points over here, like negative 3 over 2, that's going to make exactly 0. And same thing with negative 4 over 3. Those were the numbers that when we set those parentheses equal to 0, it allowed us to see exactly where it hit that x-axis. Well, negative b over 2a, negative 17 over 12, that point right there is going to be what we call the vertex. So I think I'm going to estimate that. Negative 1.41. And the output there looked like it was negative 0.04. And that's just taking me to that vertex point that's going to be very much in between those two. Now domain, if you're thinking about domain is what value you can put in for x. And really you can plug in anything. You can plug in 2, get out 70. Plug in negative 2, get out 2. You can plug in a decimal, just some random decimal, and you can square that value. I can even plug in a square root that's irrational. I can even plug in pi. And so basically this graph goes forever left and right. There is no x value that is not able to be plugged into the function, giving you some output out of it. So one thing about quadratics that we talked about in that first video, the domain for any quadratic is what we call all real numbers, meaning it goes forever left and right. That graph will continue to go forever left and right. Let's get some easier points here. Let's see, negative 1, just to give you a few points in the grid. Negative 1 gives you 1, it's right here. And negative 2 gives you 2. Negative 2 gives you positive 2. And let's see, negative 3 gives me 15. Ooh, that's already way up there. Okay, let's try what 1. What does 1 give you? 1 gives you 35. 0 gives you 12. No surprise, 12 is that y-intercept there. 1, 2, 3, 4, 5, 6. Yeah, so that u is going to be really tight, and that's because that 6 in front of x squared, when that number gets large, 6, 7, 8, 9, 10, that squeezes that quadratic together, making it really tight or stretched together. Now, domain is all real numbers. You can plug anything you want in. It goes forever left and forever right, but it never seems to go above that output value at the vertex, which seems to be roughly negative 0.04. So I want to say all my y values have to be greater than or equal to that negative 0.04. It's whatever that value was when I plugged in the vertex. Negative 17 over 12. 0.41, and that looks like it's kind of repeating 6, 6, 6, 6, 6. And so any output has to be above that, going up towards infinity. Okay? We found those x-intercepts. We said one of them was negative 4/3 and one of them was negative 3/2. And when it comes to describing the parabola as a maximum or a minimum, we're really describing that turnaround point. Is it at the bottom of the quadratic, or is it more at the top of the quadratic? So maximum is when it's kind of like an upside down U. A lot of gravity problems, something's going up and coming back down. That's because you have a negative coefficient for the x squared part. But for this one, it's more facing up forever, meaning that bottom point is a minimum. Really, it's because 6x squared, it's because ax squared equals a positive value. Anytime you have a positive coefficient, it's going to face up, which forces you to have a minimum point, and that's what I would describe this point here as, a minimum point. Thank you so much for watching this at-home series. If you have any questions at all over the summer about the videos or about any of the assigned practice work, please email me at andrew.turner@knoxschools.org. And if you're an incoming Central student that's going to be taking Algebra 1, I'll definitely see you next year. Have a great summer.